Hello, my name is Arturo Gomez from the University Carlos III of Madrid. Let me welcome all of you to this presentation about intermediate velocity impact damage on carbon epoxy sandwich panels with agglomerated cork core. A couple of years ago, the Space Shuttle Columbia reminded us about the risk of spaceflight, and particularly the impact vulnerability. On January 16 of 2003, the Space Shuttle Columbia departed with 7 astronauts on board, their mission to research about the International Space Station. 81.7 seconds after launch, one large piece of insulated foam separated from the external fuel tank and struck the Columbia on the underside of the left wing. Despite this unnoticed strike, the Columbia continued its scheduled orbital maneuvers, and during the 16 days of the mission, everything went as planned. 2 weeks later, on 1st of February, just 16 minutes before the scheduled touchdown, during the re-entry, the space shuttle exploded, killing all 7 on board. Accident investigation demonstrated that foam sheathing caused the separation of the insulation foam from the left bipod ramp of the external tank, impacting one of the reinforced carbon-carbon panels at around 200 meters per second. This created a breach in the thermal protection system, allowing superheated air into the wing structure. Nowadays, impact damage is still an active subject of research, and in this session we will be covering a specific kind of impact called intermediate velocity impact. This kind of impact occurs at velocities between 50 to 100 meters per second and can occur due to road debris or hail impact. The damage generated is sometimes not visible and can compromise residual strength and the fatigue life of the structure. Sandwich panels are widely used in fast-growing industries such as aerospace or automotive, and in wind energy. They are made by 2 strong and stiff face sheets separated by a lightweight core, what gives this structure a high bending and buckling resistance while maintaining a low weight. Carbon fiber laminates are commonly used as face sheet materials due to their specific properties. However, this material is very brittle and particularly vulnerable to impact damage. On the other hand, agglomerated cork is a promising core material against impact damage, since it can subject it to very large strains with very small permanent deformations, what gives this material very good absorption capabilities. There are multiple challenges when analyzing the impact response of sandwich panels subjected to intermediate impacts. For example, short duration of impact in the order of milliseconds. The material properties are also different along different directions, and the response is not always linear. This is the case of woven composite laminates and cellular materials. There is also an interaction between the face sheet indentation and the core deformation, since it provides a support during the impact event. The response can also be affected due to strain rate sensitivity. This is particularly important for cellular materials used in the core. And finally, damage mechanisms are very diverse and include fiber fracture, matrix cracking and delamination in the face sheet, but also multi-axial failure in the bonding in the core. Our objective is to study the behavior of sandwich panels of carbon epoxy face sheets and agglomerated cork under intermediate velocity impacts. We did that by developing an explicit dynamic finite element analysis model that included intralaminar and interlaminar damage, as well as the core's nonlinear behavior. The sandwich panel is composed of 2 rectangular face sheets bonded to a 5 mm thickness core. Each face sheet is made out of 8 plies of plain woven carbon epoxy with a symmetric quasi-isotropic layup, while the core is made from agglomerated cork with a density of 215 kilograms per cubic meter. A spherical steel projectile of 7.5 millimeters of diameter impacts the plane at impact velocities in the range of 40 to 120 meters per second. All parallel instances are modeled as a 3D deformable bodies, and the top laminate is modeled as a series of independent plies. This allows the definition of cohesive interactions. Continuum shell elements with reduced integrations are used for the plies, while 3D hexahedral elements are used for the core. The mesh is partitioned in 5 transition regions around the impact zone to provide a computational efficiency, and hourglass control and element deletion are active in order to avoid excessive deformations. The interlaminar interaction is implemented through a mixed-mode cohesive zone model. A cohesive model works under the assumption that the interface has a linear elastic behavior until a critical level of stress or separation is reached. After that, the stress transfer capacity is still maintained, but damage is initiated with a progressive degradation of the stiffness that is controlled by the damage variable d. At this point, adjacent nodes can open or slide depending on the mode of fracture. The separation at fracture is correlated with the critical energy release rate in each mode by considering the area under the curve sigma delta. The theoretical principles for a mixed mode are same. However, all the stresses and separations occur simultaneously, but they are uncoupled. Therefore, the criteria for critical stress and crack growth is given by a quadratic criteria. The cohesive model for the carbon epoxy phase sheet was validated using previous fracture testing for mode 1 and mode 2 crack growth. Two independent FEA models were developed to validate a double cantilever beam test and a net notch flexure test. Critical energy release rate GI was obtained from the experimental force and displacement curve, while the stress and stiffness parameters needed for the cohesive law, sigma I and Ki, were established through a sensitivity analysis. Both FEA models are able to predict with accuracy the damage initiation and damage propagation. Additionally, they are able to predict the unstable crack growth described in the experimental testing. The Plywood model has an orthotropic material that can sustain progressive damage and progressive degradation of the stiffness. This model was implemented through a built-in BUMAT subroutine, Abaqus ply fabric. Here, D1, D2, and D12 are the damage variables for the fiber fracture and matrix microcracking. The elastic domain is given by the activation function, that is a function of the ratio between the effective stress and the failure stress. The damage evolution is given in terms of the characteristic length of the mesh element LC, the fracture energy per unit area GF, and the elastic energy density at the point of damage GO. The material model for the carbon epoxy phase sheet was validated during previous ballistic impact testing over a laminate carried out previously at our research group. The strength and stiffness properties were obtained from the manufacturer's qualification data report. However, parameters such as the fracture energy and the shear hardening coefficient and the maximum damage had to be obtained through a sensitivity analysis too. The residual velocity after penetration is measured at different impact velocities, and the results obtained are compared to experimental values, showing a good agreement. The agglomerated cork is modeled using a hyperelastic foam model with Mullin's effect. This model is designed for isotropic and nonlinear cellular materials, whose porosity allows very large deformations up to 90%, and is able to represent the nonlinear behavior of a typical hyperelastic foam, with a linear elastic plateau and densification region. The strain energy is given by a polynomial in the terms of the shear modulus, the principal stretches, and the elastic volumetric strain. Mullin's effect is used to model the stress softening associated with damage when the material is stretched beyond its prior maximum value in the deformation history. The damage variable eta and the damage variable phi govern the response of the unloading and reloading in a path different than the initial path. Parts of the strain energy U is recovered while other parts are dissipated due to damage. From the figure, it can be noticed that the shaded area corresponds to the energy dissipated by damage, while the unshaded area corresponds to the recovered energy. This model is validated by a finite element model of agglomerated cork under dynamic compression. The response of the material is compared to previous experimental tests at impact energies between 10 to 70 joules. A four-order polynomial was used to represent the strain energy potential, and the function exponents alpha and beta were obtained by least square feet. The Mullin's damage parameters R, M, and beta are obtained through a sensitivity analysis. The results show that the hyperfoam constitutive model is able to predict with accuracy the behavior of the agglomerated cork, subjected to dynamic compression. Additionally, element deletion was implemented through a user subroutine using the Tsai-Hu fracture criteria. Results from the FEA model show that during the initial instance of impact, the panel behavior is dominated by a local response around the impact region. However, as the impact progresses, the dynamic response substantially changes depending on the penetration of the top laminate. For example, in the first video, the projectile isn't denting the top laminate. However, since its impact velocity is not high enough to completely penetrate it, the local response is followed by a progressive bending response of the panel and a final spring-back recovery of the projectile. On the contrary, at higher velocities, the top laminate is completely penetrated and the panel response considerably diverges from the initial scenario. During the initial instance after impact, the perturbation created by the projectile propagates along the thickness and in the radial direction. The wavefront travels through the thickness in the first 30 microseconds. At this initial stage, the deformation is highly localized around the impact region without any overall deflection of the plate. In the top laminate, the contact force induces a high level of actual tensile stresses around the contact region. The last ply in the laminate starts falling under tension in direction 1 and 2, creating a cross-shaped crack pattern that starts propagating radially. This intralaminar failure is accompanied by the onset of delamination in the vicinity of the cracks that propagates at almost the same extent. The indentation produced by the projectile creates a complex multi-axial 3D strain state in the core that is dominated by the compression and shear in the impact direction. The core starts failing in the vicinity of the impact region, creating a cross-crack pattern that propagates readily and through the thickness. After the initial localized deformation, the bottom laminate slowly starts deformating, and the bending response of the sandwich panel starts playing an important role in the overall response. The contact area is increased and moves away from the initial contact point towards the lateral region, reaching almost the diameter of the projectile. Intralaminar damage and delamination continues growing, but eventually its rate of growth decreases, reaching a maximum when the projectile has reached the maximum penetration into the panel at around t equal to 120 microseconds. At higher impact velocities, the projectile will not just indent the panel, but it will penetrate the top laminate and produce further damage in the core, eventually contacting the bottom laminate. During the penetration, the initial cross-shaped cracks in the top laminate start deviating from forming new cracks in the transversal direction, giving the shape of a square pattern around the contact point. Once these new cracks are long enough, the plies fracture into 4 unconnected segments with a petal shape that reduces the local stiffness of the laminate and allows the projectile to keep penetrating. The contact force exerted by the projectile on the bottom laminate creates a high tridimensional stress level in the core next to a bond line. Due to its low multi-axial strength, the core fails and a massive crack starts growing radially, reaching a distance many times higher than the projectile diameter. We can conclude that the FEA model is able to describe the impact response and damage evolution. We learn that there is an initial local membrane response of the top laminate with fiber tensile cracks and delamination that is accompanied by compressive and shear deformation of the core. And finally, we learn that depending on whether or not there is penetration, the behavior can vary substantially from a progressive bending response up to a progressive massive core damage. I hope that you have enjoyed this presentation and thank you very much for your attention.